So, once everyone's settled in, um, please welcome Carsten Nohl and Starbuck for Deep Silicon Analysis. Um, I guess we're starting quite punctual today.
Yeah, thanks. Good evening. Thanks for joining us for a little discussion on how to subvert hardware security best and how to do other fun stuff with hardware as well. Hardware defined as silicon chips, any microcontroller, microchip you can think of. Let me introduce Starbuck to you, notorious biometrics fingerprint hacker, as well as microchip hacker as of a few years. I'm Carsten, doing microchip hacking as well with Starbuck, more on the cryptographic side though, which is where I'm coming from. We're both at the CCC in Berlin at the moment, and also interested in consulting if there's any industry need in secured analysis of these kinds. We'll be talking about how to reverse hardware. And let me start with an analogy to software. So everybody here is probably aware of the process in which software is created, where a designer starts by programming source code, and then that source code is being compiled into a binary that is composed of assembly instructions, which in turn are composed of bits. There is a reverse mapping from these bits and instructions back into a domain that we could understand, that is a disassembling tool. So this design process goes both ways, and everybody who's working in security is aware of the fact that especially the reverse way is very important to do security analyses on other people's designs where they don't openly share the source code. So the reverse way is crucial for security. In the hardware domain, however, this reverse way unfortunately doesn't exist yet. There is a similar design process in which a designer creates some source code in different programming languages, but still pretty much just hacks the design into a computer and then compiles it with a place and route tool into an actual chip that is being built from logic gates, which in turn are built from transistors. Now the reverse mapping is what we want to provide, and we'll be releasing bits and pieces of it today, and hopefully enough for some of you to get involved without deep hardware knowledge at reversing hardware. The process that we'll be explaining throughout the talk has the following steps. We start with a silicon chip, really any microcontroller or smart card chip, for instance. We'll take off micrometer by micrometer of this chip to take pictures then with an ordinary microscope. We'll stitch those pictures together to have basically a floor plan of the chip. That would be the equivalent of your binary. We'll use these chip images then to find instructions, or what we call logic gates, using pattern recognition, and also the connections between these instructions, what in the software world will be the control flow. Finally, we'll try to interpret what these logic gates mean and what algorithm is meant to be implemented using those circuits, right? And we do reach at enough of a description of an algorithm to, in our case, be able to break it, or to be able to do whatever you usually do as the last step of reverse engineering. Now, Starbuck is going to go ahead now and talk about the first couple of steps. This is here, okay? Yeah.
Yeah. Okay. Before you can start working on the chips, you have to get to the chips. So normally, these chips are in some kinds of plastic card, as you can see on the left side. There's an RFID chip with an antenna around here, and where the antenna at the ends of the antenna there's a chip. So first of all, you had to extract the chip out of these plastic cards. So the chip cards are made up of polycarbonate. So the best way is to use acetone. So the acetone will dissolve parts of the polycarbonate, and you will get to the chip. But most of the times the chip is not completely blank there, but it's still encapsulated in epoxy. So there have to be another step before you can get the bar chip. And for this one you will need fuming nitric acid. It's a very bad acid, so normally you shouldn't do it at your kitchen, but send it away to a chemical laboratory or something like that. If you have, sometimes the reseller, the manufacturer sells also blank chips, so if you can get your hand on a blank chip, then you should buy this one. So to understand the next steps on the next slides, first of all, how does such a chip look like? And we start on the bottom. It's a bar silicon wafer, and on top it begins with a transistor layer. So there's a gate, source, and drain over here, and those transistors are connected on higher level, on higher layers, calling the metal layers, with metal wires. So as Carsten already mentioned, our work is to polish to each individual layer, making photos, and then try to find out the function of the implemented crypto algorithm or something like that. How to polish to these layers? We started with doing it manually, but there's much better ways to do so with an automatic polishing machine, as you can see on the top right side. So it's just a spinning table, and you put some polishing liquid on it, and it will polish the silicon chip at to the layer you want to have it. And there's generally a problem. These chips have on top of it there are bonding pads. So if you put this upside down to polish it, it will have a tilt. So the solution for that problem is to take some plastic block which fits in the polishing machine holder and glue it with the backside to this block, because the backside is very parallel to this active layers we want to polish in.
Let's point out, though, that this polishing machine is absolutely not necessary. Nice to have, but we have been doing fine with the finest sandpaper and a vibrating surface at my university. So this is deluxe equipment. You can definitely do with less fancy stuff.
So we started with polishing equipment from a optical fiber laboratory. So everything below 1 micron and grain size of the polishing liquid or polishing paper should be fine. There's another possibility to get to the single layers, and it's called etching, wet etching with hydrofluoric acid. But the hydrofluoric acid will go to the silicon dioxide, which is an isolator between each layer. But as you can see on this picture, there's a little problem to exactly get to or to get to one exact layer. So normally we will dissolve some parts between layer 1 and 2 and between layer 2 and 3. So you don't have a complete layer etched away. Hydrofluoric acid is only very useful to get nice pictures of the lowest level of the transistor layer, as you can see over here. So after the polishing or etching, you have to make pictures of the chips. So at this structural whites we are actually working on, we still can use optical microscopes. So magnification between 500 and 2000. It's what we are using right now. Yeah, the interesting part is that every part of this process could be done with equipment which is really cheap. So the most expensive part over here is a microscope, but if you are interested in playing around with microchips, $1,000 shouldn't be too much to invest.
Yeah, let's mention though that this only gets you chips up until like 5 years ago. Everything that's manufactured in a newer technology, you need better than optical microscopes for. Yep. So if anybody has access to a scanning electron microscope or anything of this type, we definitely need you to get involved in this hacking to take some nice pictures, high resolution at sub-optical magnifications.
Exactly. Yeah. Right now, also the last chip we were working on was at a structural white around 300 nanometers, and everything below the wavelengths of visible light, so everything below 500 nanometers, it's nearly impossible to look at with the optical microscope. There are some special kinds of optical microscope called confocal microscopes. The advantage of these confocal microscopes is that they can make sharp pictures of each individual layer. As you can see on the right side, there are the blue one, and is the top layer, the top metal layer. The yellow stripes down there are the second metal layer, and down there is the third metal layer. Yeah, and if you have only 2 interconnection layers, you don't really need to polish to that layers if you have a confocal microscope, but they are still more expensive and not very easy to use. As Carsten already mentioned, below 500 nanometers of structural white, you will get to other kinds of microscope, for example, the scanning electron microscope, or as you can see here, a focused ion beam. With this kinds of microscope, you have magnifications up to 20,000, 50,000, so there shouldn't be no limit right now to have a look at newer chips. But also, like the confocal microscope, this kind of equipment is really expensive. Yeah, next step, if you have the pictures of each layer, the single pictures, you have to stitch it. The problem is with a normal camera at this magnification on the microscope, you will get images, image sizes of around 100 by 100 micrometer. And for a chip of around 1 square millimeter, we have 10 by 10 or 20 by 20 single pictures, single images, and they have to stitch together. We did it with a free tool called Huggin. That's a tool from Panorama Photography, but it was not really easy to handle. So Sven wrote a really cool program which is doing exactly the stuff which Huggin does, just stitching pictures together and get rid of the tilt of the pictures. And yeah. Carsten will show a slide demo.
Do you want to show it? I can. Yeah, so thanks to Sven Karten for bringing this tool to us. It does what Huggin is supposed to do, only it does it right for our purposes, that is. I'm sure Huggin has its user base. So here we're looking at 2 pictures that have a slight overlap, and we want to stitch those together into one picture. So the pictures have to not only be moved on top of each other, but one has to be slightly rotated because you'll never get them perfectly parallel. You start off by setting 2 control points. So you see this structure over here is the same as this over here, right? So we set a control point at this dot, and we'll set it again on this side. Slightly adjust it with the arrow keys, and we'll move on to the next control point. Should be as far away from the first one. So down here, we see this structure here and here. You guys see that? That this is the same dot? So we click here, we slightly adjust it. I think this is pretty much perfect. Yeah. And it did stitch it. And now I would like to point out to you where it stitched it, but you can't actually see it. Oh, yes, here. So you see this one dot up here, that's where it stitched it together. And you can't see any deviation at all. So this is so much better than the tools we've been using so far. So thanks to Sven for creating this for us. This is GPL online. The URL is at the end of the slides. Moving ahead, should I be covering this part? So yeah, now moving ahead to the second part of the reversing process, the recognizing structures in the images we're taking. Let me first point out that a chip is full of patterns, recurring patterns. Whenever the same function is used on a chip, and there's only very few functions, then the same instantiation of this function is pulled from some library. So very similar to assembly code, where the same instructions will be occurring over and over again. These are the assembly instructions. So this function, for instance, occurring 4 times in this image is actually the same function pulled from a library. And wherever the structure, patterns, the computer can be tremendously helpful in recognizing those. In the case of these gates, we just use face recognition software. We tell it up here, this is a face, where are other faces in this picture? And it will find all of these. We do that for every single logic function, and we get a map of where on the chip the logic functions are, right? So that doesn't yet tell us what these logic functions are, but at least we know the families and where they're spread out. To find the functions themselves, we have to look into one of these cells and figure out how the transistors are connected to each other. To anybody who ever did VLSI design, this is trivially recognizable as a NAND gate, as is this, as is this. They're actually very similar. You can in each of those see the same setup of the 4 transistors. If you haven't studied VLSI ever, no worries. These are reoccurring on every chip, and we documented a couple online already. So no need for you to learn it. If you do come across a new chip, though, that is slightly different from what we already put online, send it to us. We'll document it and put it online for you. So you don't have to worry about recognizing these structures. Basically, we are writing the assembly language manual here. As a last step in interpreting in recognizing the structures, now that we have the map of where what function is, we need to see how the functions are connected to each other. So in assembly language, the control flow, where are things jumping, where's data passed along through the registers and so forth. These are just metal stripes that we've been seeing in a picture earlier that are connecting these different logic function blocks. And there's several layers of those, and they can be interconnected, and it's just a huge web of metal connecting blocks. Of course, the computer, again, can help us here tremendously, because this is very cumbersome work. And we did implement a tool that applies a bunch of filters to figure out the most likely location of these metal wires. Thanks to Christine Schulz, now we have a tool that's fairly reliable in recognizing these structures. As the next big extension of the D-Gate tool we'll be introducing in a minute, this will be integrated into DGate and then combined with a lot of meta logic information to become even more accurate. So we are fairly confident that we can even recognize small metal wires on large chips where we only have bad pictures from using an overlay of many filters plus this meta information. That's going to come as a DGate extension later this year. Now, we've been talking about this DGate tool a couple of times now. Thanks to Nitram from the CCC in Berlin, this has all been, all our knowledge, all our little scripts have been packaged into this very powerful tool that I think Starbuck is going to demo now. Nee, ich habe es ja gar nicht festgeschraubt. Are there any questions so far? Does this all make sense? Does this seem like something you could be doing at home? If not, ask questions now because you can do this at home. Then if you think you can't, you didn't understand parts of it.
I would like some more information about how you decapsulate the chip. And do you know about any source where you can online learn the design of the chips so you can also reverse them? As you said, you...
Well, that's 3 questions. Let me answer them in order then. How do you decap chips? You throw them in an acid and wait for a few minutes. The acid preferably being fuming nitric acid at a high temperature. This will take off any plastic surrounding the chip, but not attack the chip itself. Very straightforward. If you're not good with chemicals, I'm not good with chemicals, send it to a lab. Any laboratory will do this. We are paying something like 40 euros for a batch of chips to be decapped. Your second question was, how do you online learn about how to design chips? Just Google for VLSI design book or something. There's plenty of resources on doing that. Now, your last question was, how do you learn about reversing chips? And the only real resource we ever found on that is a book that's about 25 years old by a Siemens engineer, so it's in German. And to my knowledge, there's nothing more recent than that. We are trying to get more attention again on these issues and try to get more people involved. But things are moving relatively slowly as we're still just a small research group in Berlin. We released the tools now, so maybe somebody who's more gifted in documenting things will pick up the tools and then write a nice book about it. Was there another question here?
Karsten.
Yeah.
One of the challenges that we face when we're doing, for instance, fault injection on the more secure microcontrollers is glue logic, where they more or less randomize the whole layout. Is that something that this tool can also reverse engineer, or would you have?
Of course, yeah, especially that.
Yeah.
We're not looking at things like find the data bus. I mean, somebody like Chris Danofsky, with all his 40 years of microchip in his head, he will spot a data bus before we even get our microscope running. We are only looking at glue logic, and we are reversing whole blocks of glue logic, these custom ASICs that everybody is so fond of now. Yeah, well, we're looking at the 66 memory encryption, for instance, at the moment. Yeah. Very widespread security technology, never really documented or broken by anybody. Yeah, should not be difficult.
Yeah, sounds very cool. I'm definitely going to try your tool. One of the things we've also been working on is the stitching, actually, with the Hugging tool. And I found that you can actually force it into stitching it the way you want.
By setting the angle very tight.
Yeah, you can actually script it more or less and then change that.
I think the Hugging is just overkill for us.
Exactly,
Since it tries to bend things in a 3-dimensional space, we don't need all that. We just need
you can force it not to do that, actually.
Say that again?
You can force the tool not to do that by setting it. But
well, we have our own tool now. Maybe we'll find.
I'll have a look at that as well. Thanks.
Cool. Thank you. So here goes the DGate reverse engineering.
But what you can see here is the Logic chip. Logic is used like MyFair for securing buildings or entrance control. And this Logic chip has around 500 single gates. What you can do with the software is, first of all, you can select a target. On this side is a flip-flop, and after selecting it, you can create a template. So the template is used to later on automatically recognize the same flip-flop over the whole chip. It's already done, so the next step, if you have created the template, or maybe you could found the template on silicon-zoo.org or something like that, so it's a standard library. You go to template matching and select this flip-flop. I have some different parameters, and after half a second, it also found the flip-flop over here, which I deleted before. After that, you have to select the different ports for this flip-flop, or for all the gates. And the last step is to the metal tracing. So if you want to know which port is connected to this D entrance of the flip-flop, you have to switch to the upper layer and follow the trace, going down again. So you normally have to do this on a big screen. And as you can see, it's still really complicated, so automatic metal tracing would be very nice. So I guess I lost it.
If you buy a microscope today and get started at this, we promise we have metal tracing automated by the time you need it.
Yeah. Okay, going on this way, up to here. Again, one layer to the above. And so it's connected to the output of this NAND. So, and as I already told, there are nearly 500 single gates. So we have nearly 1,500 to 2,500 of connections between each gate. So it took us, I don't know, maybe a week to trace a whole logic chip. So it's not that complicated, and it could be done by a lot of people, and then afterwards merging the results.
Right. And the logic chip is relatively small, probably about the smallest you'll ever find as a microchip. But even if your target is a much larger chip, you'll never want to reverse the entire chip. As I was saying, for instance, with the 66 by Infineon, a very, very popular microcontroller, you really only want to know its memory encryption, because that's its security function, the one that's least subverted so far. And that is about the size of this logic chip, a little smaller even. So even manually, you can easily do this within a week. And with the added automation, this will be a 2-day job for somebody. Now, yes, this was the DGate tool. Thanks to Nitram for bringing this to us. Let's now quickly cover the last step of the reverse engineering process, the interpreting those connections and gates and all that the DGate tool gave you. Since we don't want to do more work than absolutely necessary, we first want to limit down our scope to exactly those functions we want to reverse engineer. And in our case, that's mostly cryptography, in which case we look for linear feedback, shift registers, XOR, and that type of function, or it's instruction ledgers. The Pirate TV hackers will know why you want to find the instruction ledgers. But suffice it to say, if you knew where those are, you can read out the entire memory of even a secure chip usually. So we want to find a small set of ledgers. And of course, once we have the map, we'll just find 16 flip-flops that are close to each other, and probably 2-3 areas where the instruction ledgers might be, and limit our focus to exactly those. Once we know what we want to target exactly, we'll run on those areas consistency checks. Our tools are not 100% accurate. They hopefully will be close to that soon, but we still want to make sure there's no errors. And errors don't go undetected usually, since they will lead to, they will violate some logic rules. For instance, that two outputs may never be connected to each other. That would be the most simple logic rule, because then they'll fight for the value, right? Simple rules like that. We run these checks, and once we're confident that the information we're looking at is actually consistent with all these rules, we'll inspect it. And that is pretty much a manual process, much like IDA Pro is at some stage, where we just compile different small blocks into bigger blocks and try to reassemble the algorithm as it was meant to be represented by the original designer. For instance, find the different building blocks of a cipher, which is the example I'll show in a second. So does that make sense as a process? So there's some manual work involved, as will always be with reverse engineering, since the computer will never know what's the most intuitive way of representing it to us. But most of the other steps in here will be automated at some point. Now, to do this manual inspection, we have a new tool too, thanks to Daniel Widekind and Stefan Skillen. This is just a viewer tool, really, that helps us tremendously in moving around the circuit, drawing boxes, grouping things eventually, and just having a much more intuitive way of interfacing with this netlist data, which, as it comes out of the DGATE, is just a large XML file. So this helped us very much already. The way we've been hacking chips so far is with pen and paper, really. This is some part of the Logic RFID chip. And once Starbuck was done with tracing all these wires in the DGATE tool, he came over. And how long did we take to draw this out? Maybe an hour? 2 hours, yeah. 2 hours at most, maybe. I would say an hour plus an hour of drinking coffee. So that's how long it takes then to find a cryptographic function. Granted, this is a very small cryptographic function, but one afternoon should definitely suffice once you have the information in the DGATE. And then it took me another hour to convert it into this beautiful PowerPoint representation. Well, so if you count the boxes, there isn't very many. Each of those is one bit of state. Clearly, this is insufficient state for any security primitive. So we hereby declare Logic prime RFID tags to be completely insecure from a cryptographic point of view. After running DGATE for some time and sitting down for an hour documenting what this tag does. As further motivation why you should get involved, we did look at a bunch of chips and found all of them to be interesting from a cryptographic point of view, some of them to be severely flawed. Some of you might have heard of the MIFARE and how it's not all that secure. The Logic Prime is another instance. We had a talk this morning about the NXP high-tech RFID tag. That's not secure at all. There's others that are slightly better, like what we use in cordless phones, the DECT phones, or what some payment cards in the States use these days, but it's still not cryptographically sound from an academically point of view, I would say. So there's huge interests by cryptographers to look at these ciphers and to figure out whether or not they're secure. And we mostly just want to enable them to do these analyses. And it has been a lot of fun doing this, and I would hope some of you will want to get involved too. So this list on the last slide was fairly short. There's bunches of other proprietary systems that yet need to be documented, and we feel like there's definitely enough fun and publicity in it for a lot of you to want to jump at this. We know that, that everything that's kept secret, as in cryptography, proprietary, is usually weak or tends to be weak. So help the cryptographers get at this data. We would eventually want to see, of course, for microchips that we are asked to trust, as in a trusted platform module, to go through an analysis like this. So far, all these chips with the security certificates do not experience a high level of reverse engineering. There's very small sections of reverse engineering in the common criteria standard, but it's mostly intrusive fault injection or side channel attacks. We will want reverse engineering to become more common again in the design of microcontrollers to point out design flaws like the ones we found early on in the chips we are asked to trust, right? And with that, I think I saw a 10-minute flag, so we definitely have plenty of time for discussion if there's any questions. Oh, well, just a quick heads up. If you do want to get involved, not just in hacking your own chips, but actually help us make this process even more streamlined, there's plenty of work, especially for programmers. Extending dgate, further automating things, extending it perhaps to your custom designed Amiga chip from the 80s. We get requests like this all the time. So there's different domains of chips that we can't break yet because they're just way too old. And people, in fact, don't want to break them really. They just want them to be documented somewhere. Beyond programming, we could also need some mechanical help. Turns out that the most expensive piece of equipment is a little stepper, a little XY stepper to put under the microscope. It's ridiculously expensive compared to the whole microscope. So if anybody has an idea of how to create one cheaply, like the RepRap, but maybe an order of magnitude finer.
Take an old hard drive, then you have a linear drive, and if you apply DC to the coil, it moves in one or the other direction, okay. and then you should get some position, and so you can make a mirror and maybe some CCD scanner line, and then you know where it's moving, and so this would be one construction. So you can move a lever from left to right, and so you make this 2 times, and so you have an XY. Drive that is a little bit. It has cylindrical coordinates, so you have to be a little bit calculus, but it's a cheap solution.
Yeah, it should work, but we need a really low resolution, so about some microns.
But the hard is it.
A hard drive makes this. Have you seen a 50 gigabyte hard disk? It has a very fine resolution,
okay.
Because a voice coil has an indefinitely fine resolution.
Well, the idea of using a hard disk came up before in this context for the polishing, to use the rotating surface to polish your chip. So we can take apart the hard disk and recycle every part of it.
This was invented before. Go to Antwerp, look at the diamond grinding machines. They look like this.
Exactly, yeah. Thanks for the idea. We'll definitely look into this. So yes, please get involved on the programming side or with ideas like this. We definitely want to extend this to more domains. And with that, finally, I want to thank you. Send us questions by email, download the tools if you're interested, or ask questions now. Thank you very much.
Thanks.
Should we give people a chance to ask questions? Kannst du gerade noch warten?
We, no, maybe.
Should we get questions from those people first?
Well, I have a funny question about online banking. You know, most online banks, banks in general, which have an online service in Holland here, use some sort of cryptographic device, which you have to insert your banking pass in.
Right.
and they have some sort of hardware crypto loop which requires a challenge from the website and a pin key, and that gives you a response, and that should authenticate you.
Yes.
How safe is that?
Well,
That's really the question.
They're hackable, but probably not hackable to a degree that would concern you as a customer of a bank for online banking. There's always a way of extracting all information from a card to make a clone of the card. In a process, of course, you destroy the card. So if you give your banking card to somebody and allow them to hack away with it for days, they'll have a clone of it. In the meantime, of course, they could already have used the original card you gave them to steal money from your bank. In many applications, breaking doesn't mean compromise.
I didn't mean the banking card. I meant the cryptographic device which you get from the bank.
I mean like an RSA hash chain secure ID.
The label doesn't say what cryptographic system is used.
That every minute shows a different number? It's called the secure ID. It's cryptographically sound as long as the information stays in it. Again, if you give somebody a couple of days to hack away at it, they can create a clone. In the meantime, though, they could already have used the one you gave them to hack into whatever you're trying to protect. So yes, if you lose physical control of these devices and somebody is determined enough, as in $100,000 to hack it, then they'll do it.
But this device is generic. It is not bound to a person, you know. You have to insert your banking card in it. That should physically identify you. So these devices themselves, these cryptographic devices themselves are generic. You can get them, well, for like 20 euros from your bank.
Well, there will be a secret involved at some stage, and it will be extractable if you give somebody a couple of days' time in the lab and allow them to hack your card, in which case they could have already stolen your money.
So they're not safe.
So yes, they're hackable, but not of concern. Banks usually use standard cryptography, and you're only concerned with protecting the secret keys. You're not so much worried about the secret keys leaking through bad cryptography.
What he meant was just a bogus reader that reads the smart card, and you can enter your key in the reader, and then it eventually reads the smart card. That's the whole idea. Yeah. Yeah. Yeah, but you can easily reverse engineer it. Yeah.
Any other questions?
I have a question about the pattern recognition algorithms. When you're recognizing a gate on a chip, can you take it back to the VLSI program that generated it and figure which program the engineer used to design that chip?
Well, we can't figure out what was used to design the chip. No. Well, we can recognize the library. Most often what happens is the person designing the chip doesn't even know what the gate looks like. So in his tool chain, there is no such thing as a fully specified gate. It will draw a block saying, put a 2 NAND here. It will send it off to the foundry in the standard format, and only in the foundry, these black boxes will be filled, right? Yes. We can, of course, see when it's using the same library, the same foundry, right? Those will use the same patterns.
Sure. I guess the thought might be, if it was known that a particular library had a vulnerable random number generator that gets implemented down into logic, you could...
Well, these logic blocks are completely verified. There's no such thing as a broken inverter, right? And the random number generator is always composed of different parts on the gate level, right? Of course, there might be some IP block, a broken random number generator that different manufacturers use. That's not the level of pattern that we recognize, though. We could. If we looked at very similar chips and only wanted to recognize the difference, we would probably go down that road, but we haven't yet. Thanks for the question.
So how usable is it? Because I want to reverse engineer FPGAs, old ones, and the problem is that we need some automated tool because nobody would like to point and click and look for metal layers. So I want to have a netlist, so I can make the logic from the FPGA.
Well, I can't see why an FPGA is any different from any other chip. So you can already use the existing tools, or you can wait a couple of months, have it more automated. An FPGA is huge, but highly, highly structured. An FPGA has the same structure thousands or millions of times. So you reverse engineer it only once. Tiny piece of your chip, you reverse engineer, you know how the rest of it is working on a cell level. So it's probably a good target for this. The most recent FPGAs, though, you won't be able to optically take pictures of.
We wanted to take old Xilinx FPGAs because the patents are run out, and so it's possible to make something interesting with them. And so there was a famous FPGA, it's called the 6300. It was partly reconfigurable, and so Xilinx doesn't produce them anymore. And they're very sexy FPGAs, and so we want to make them our own.
Well, being able to reverse engineer it doesn't yet mean that you can reproduce it, right? So probably you're out of luck trying to assemble anything beyond a very simple circuit yourself. I've been producing chips at my university. It's something upward of $50,000 for a single run, and you get tiny, tiny chips for it only. It's very costly. A chip fab is a couple $1 billion right now, so you need to know somebody who owns one pretty much.
If you take an old process, maybe 0.35 nanometers or something, micrometers. So old processors, for example, that were used for 10 years ago or something.
Well, they're not being used anymore. So yeah, we can chat later. Yeah. Those factories just don't exist anymore, right? Sorry to disappoint.
Are you seeing attempts by the chip makers to prevent this kind of attack, such as obfuscation or something?
Of course, yeah. There's a couple of ways they try to make reverse engineering much harder. They only look at manual reverse engineering, though. People that look for exactly the instruction ledgers that I've been talking about, that will put those in as random of an order as possible. With an automated approach like this, if all you're interested in is find out what function produces a certain output, it doesn't really matter in what order the gates are or how weirdly they're connected to each other, whether there's fill logic that doesn't contribute anything. The tools will just find the core that produces the functionality and will print it out in a nice circuit diagram. So all the obfuscation they put in tries to defeat human intuition, as in these should be in order, they're not, so I give up. The tools don't really have a concept of intuition, so they don't care.
They're adding a cover layer on top of it to prevent making pictures directly to the chip, but it's just another layer, so you can polish it off and make a picture of the layer below it, so it's just one step more.
Yeah, but as I was saying, Common Criteria is considering putting more reverse engineering protection requirements into the EAL certificates. So it'll be interesting to see what they think prevents what we are doing.
I missed most of your talk, but how many metal layers can you actually do? And if you polish them off, how do you do the coplanarity of the layers? So you're not like polishing off half of the next layer and then you're not getting images. So
the chip with the most numbers of layers was the MIFARE chip. It was had 6 layers, but you are not limited to any amount of layer. So if you're trying to flatten the chip so it's not tilted, but if it's tilted, you will polish half of the chip, making pictures, and polish the other half and making pictures and stitch it together. So if it's not totally untilted, it's not a problem. It's only a problem if it's an angle of 1 degree or so. But otherwise, it's not a problem to also reverse engineer up to 8-10 layers.
Yeah, but a chip that has 10 metal layers will probably be way below optical resolution. So we need completely different imaging tools. And we can just as well do plasma etching then if we already go to expensive equipment. So in which case we don't worry about tilting at all.
So maybe you can make the pictures, but to tracing the lines over the 8 metal layers, it's nearly impossible to do it manually, and it's also really hard to do it automatically.
You mentioned reverse engineering trusted platform modules. Did you find any attempts of building in backdoors?
Building a what?
Backdoors into the chips.
Oh, we haven't reversed TPMs in their entirety yet, but what we have been seeing is that TPMs are pretty much standard smart cards with some added functionality with some more meshes. So whatever attacks are possible on smart cards are pretty much possible on TPMs. Do intentional backdoors exist in smart cards? I don't think so, but there's enough unintentional ones. As in, trigger this debug pin and I will tell you my password, this type of a backdoor, right? But I don't know if you would call it a backdoor, just a design flaw.
So we found some parts that looked like fuses that had been cut afterwards. So maybe that's something you can connect, a debugging port or something to bypass the password. That's possible.
Right. Check out FlyLogic's blog, FLI Logic. They have a nice documentation on hacking smart cards, and most of which should apply to TPMs as well.
What image analysis software did you use?
What's that?
What image analysis software did you use?
What image analysis
yes.
software? Well, initially we did everything with MATLAB filters. By now everything has been rewritten from scratch in C by Nitram, who sits 2 places behind you.
Anything else?
Okay.
Okay, then thanks for your talk, especially Carsten for your talk marathon today.
Thanks.